Okay, we are now on the air. Okay, all right, guys. So they just tried to find the inverse of a function, and we just made a little note that the notation for the inverse of f is f to the negative 1 of x. But that notation, that little negative 1 exponent, does not mean the same thing as if the negative 1 was on either a number or a variable. When it's on one of those, it just means the reciprocal. But when it's on a function, that means you're switching all the x and y coordinates. So, what did we do to get the inverse again? We switch them, right? So we have x equals y squared. This is the inverse. And then we solve for y. When you solve for y, what do you get? Yeah, normally you say plus or minus the square root of x. But it has to work out to be a function. For each x, there can only be one y. And that's why they told us this. If on the function the x's were greater than or equal to 0, on the inverse, what has to be greater than or equal to 0? The y's, right? Because you've just switched them. So that's why we don't take the negative square root. So our inverse, f to the negative 1 of x, is equal to the square root of x. That's the inverse. And if we graph the square root of x, these graphs, the function and the inverse, they're symmetric about what line? Do you remember? Y equals x. It's all coming back. All right, so now we know the inverse. Let's say we take 4, and which one am I going to plug it into first if it's written this way here? The function or the inverse? Well, you work your way backwards, right? This just means the inverse of f of 4. So first we plug the 4 into the function. If you plug 4 into the function, what do you get? 16. So f assigns 4 16. Now, if we take that answer and we plug that into the inverse function, what are we getting now? We're back to 4. So if we take 16 and plug it into the inverse, we get back to 4. Let's work in the opposite direction. Just change this to full. Now let's start with 4, and we're going to plug it into the inverse 4 first. If you plug 4 into the inverse of f, remember that's the square root of x, what do you get? 2. Good. Now we're going to plug that answer into the function. 4. See what happened both times? Whatever a function does, the inverse undoes. Okay? Whenever you take composition of a function and its inverse, it doesn't even matter the order. You're going to get out whatever you put in. So, if we look at our next little example, in C, they ask us for the composition of a function and its inverse at x. Either order, what do you know you're going to get out? X. Now, this can be really, really helpful. Because suppose you have, as we have in D, f of x equals y. And we want to solve for x. I don't want that function there. I want to have just x. What can we do to both sides to get rid of a function? Take the inverse. Do you see that? So if I take the inverse of both sides, bless you, what is the left side going to be? Just x. Have you ever seen that before? I know you have, but I don't know if it was pointed out to you. Let me ask you, when you had something like this, sine of x equals 1/2, how did you get rid of that function? What did you do? The inverse what? looked at the inverse sine. You hit on your calculator second sine, which is the inverse sine, right? What you were really doing was you were getting rid of a function by taking the inverse of that function. You never saw this side. You would just write x equals, right? And just for fun, what is the angle whose sine is a half? Do you remember that? 30 degrees. What is that in radians? Well, 180 is pi. So is a fourth of 180 30, or is a sixth of 180 30? A sixth, right? So it would be pi over 6. So inverse functions are great because they can help you solve for an argument. You want to get rid of a function, you take the inverse to both sides. And today, what we want to do is find the derivative of an inverse function at a particular value. I'm wondering if I should just do that first, or, you know what, I think I'm just going to do that first, and then I'll go to the homework, because it's not long. Suppose I want to find the derivative of the inverse function of f at some value b. The most direct way to do it would be get the inverse. Put it away, Tim. Get the inverse and then take the derivative and plug in b, right? Here's the thing, especially on the AP exam, you're going to make it so when you switch x and y, you're not going to be able to solve for y. They're going to make it challenging, so you're not going to be able to do it that way. So I have to teach you another method. And it's going to take a little bit of thought on your part, but you can do it. Suppose I have some function that I have here in the upper graph. This is y equals f of x. And its inverse, remember all an inverse is you switch the coordinates of every single point, is the lower function here. So the upper function here is f of x, and its inverse is down here, f to negative 1 of x. Because it's awkward to write f to the negative 1 prime, let's just call the inverse of f g of x. So what we want to find is the derivative g prime of b. We want g prime of b, which is the slope over here. We want to see if there's any relationship between the slope over here on the inverse and the slope over here on the function. Okay? And we're going to try to think it through. If this is the point BA on the inverse, when you switch the x and y coordinates, you got AB over here on the function. Does that make sense? Okay, so if BA is on the inverse, AB is on the function. Since g of x is the inverse of f of x, all the x and y coordinates of the points on the graph of f are blank on the graph of g. So think about all the points on the graph of f. I don't want to say opposite, because then you'll think like negative a, negative b. Okay, you can say interchanged or switched. What word do you like better? You like reversed better? To me, I'm just going to back it up. I don't know. I'm going to say either switched or interchanged. Switched is actually shorter, but maybe you'll read that. Okay, so one thing that we know is that all the coordinates of the points on the graph of f are switched on the graph of g. The other thing that we know is that slope is defined as the change in what over change in what? Change in y over the change in x. Excellent. So we know slope is a change in y over change of x. We know to get the inverse, you've switched all the x and y coordinates. So you've switched all the x's and y, and slope is the change of y over change of x's. Do you think these slopes have any relationship to each other? These are the two clues I'm giving you here. To get the inverse, you've switched all the x's and y's. And we also know the slope is change of y over change of x. So if you switch the x's and y's, how are these slopes related? What kind of inverse? y negative. You've switched them. You're almost there. You're so close. Slope is change of y's over change of x's. You've switched the x's and the y's. So the slope's not going to be the same. Okay, so what do you do to the other one's slope? Reciprocal, that's the word I'm looking for. Oh yeah, I knew you would get it. So you want to kind of see, like I want to go back to the picture so you can really appreciate it. That's reciprocal. It's really bad handwriting. But so if I know that the slope over here at A is 2/3, let's say, so I know f prime of A is 2/3. What is the slope over here at B going to be? 3/2. So they're not negative reciprocals like perpendicular lines. They're going to have the same slope, the same sign. Slope's going to have the same sign. But their slopes are going to be reciprocals. So if I want to, this is what we're trying to figure out now. So if I want to find the slope over here on the inverse at B, I can just figure out what the slope is on the function at A, and then flip it. You know, we're not going to be given the inverse. You're going to be given the function, and you're going to be asked to find the derivative of the inverse at some x value. First thing you're going to have to realize is, okay, well, if x is b on the inverse, y is b on the function. Solve for x, find the slope there, get the derivative, plug it in, and flip it. That's going to be our method to get the derivative of the inverse. It's like a 4-step method. So I want to start with the one that we've already seen, the do now problem. Oh wait, I have to finish this one up. So we said the derivative at B of the inverse is 1 over the derivative at A. And since f of A equals B, what does A equal? If we wanted to solve for A? Very good. Would be the inverse of f at B. So this is the formula that you'll see like when you look in the textbooks for the derivative of the inverse at a value. It looks so complicated like this, but wait till you see the 4-step approach. It's really not bad. Okay, so I just want to show you, we'll do 2 examples and I'll go back to the homework. I laid out the steps here for method 2. So we're going to basically, we got to find A. We got to set the original function equal to whatever B is, solve for x, that's like our A, get the derivative, plug it in, and flip it. So if our original function is y equals x squared, the first method, which you're never going to be able to use, would be actually get the inverse. If you're looking for the derivative of the inverse at 4, get the inverse and take the derivative. So let's do that. Since we already have the inverse, do you remember what the inverse of x squared was? So yeah, it's just square root of x. And we're calling it g. It makes it easier. So if we took the derivative there, what's the derivative of the square root of x? 1/2 x to the negative 1/2. So it's 1 over 2 rad x. And we want to know what is the slope of this inverse function at 4. So now we could just plug in 4. 1 over 2 rad 4. What does that equal? 1/4. So it would be nice if we could always just get the inverse and just take the derivative and plug in a number. But I want to show you the other way to do it with this one. So the first step is to figure out your A value. What you do is you set the original function equal to the x value, because this is like y on the original function. So the first step is you set your original function equal to your B value and solve for x. Now x, if you recall, has to be greater than or equal to 0. So what does x equal? 2. Good. Your second step is get the derivative of the original function. What's the derivative of f? Now we're going to plug in the value we found into that derivative. So we want to find f prime of 2. So plug 2 into the derivative. What do you get? 4. Good. And now all we have to do is flip it. So we wanted, recall, we wanted the derivative of g at 4. It's just going to be the reciprocal of that, 1/4. We never found the inverse function, and yet we know the derivative of it at 4. Yes? Oh, we took the derivative of f. Okay? See how we're getting the same answer? And it's one. Yeah, one way we actually got the inverse, took the derivative and plugged in 4. The other way we said, all right, well, let me just work with the original function. Let me figure out the x coordinate on the original function. So let me set the original function equal to 4. You basically found out that a is 2. You found the slope over there and flipped it. Yeah. And then I plugged in the value they gave me into the derivative. That would always work if you could find the inverse of a function, if you could write what it was. So switch x and y and solve for y. But this is like the cool AP way. Yep. So the second method, we wanted the derivative over here at 4. So first we said, okay, well, let's work with just the original function. That would mean that y on the original function is 4. So we solved for x. We set x squared equal to 4. We got 2. We found the slope of the tangent over here, which was 4, which meant the slope of the tangent over here had to be 1/4. So we worked with so we found that the slope over here was 4, which meant the slope over here had to be 1/4. I know, barely hanging on. Let's just try like another 1 or 2 and then I'll. So in these problems, what we want to do is figure out what is the derivative of the inverse of this function, in this first case at 9. So what's the first step? We're only going to use the second method. Well, that'll be the second step. First thing was we got to figure out what x we're talking about, because this x for the inverse is the y for the function. So your first step is you got to set your function equal to the x value they give you. So what does that make x? 2. Good. Now, again, we're never going to get the inverse. We're just going to take the derivative of the original function. What does that equal? Nice. We're going to plug in the value, the x value we got, into the derivative of our original function. So step 3, we're going to take f prime of 2. So 3 times 2 squared equals 12. Good. So if the slope of our original function at 2 is 12, what is the slope of the inverse at 9, where they asked us? 1/12. Because we're trying to avoid getting the derivative of the inverse. And because those slopes are related, the slope over here, well, with these examples, in this example we just did, this is like a 9, okay? The x coordinate here, we want the derivative is 9. And what we said was, well, we got to work with the function over here, which means that its y coordinate is 9. So we set the function equal to 9 to figure out the x to work with. So that was our first step. And then we found the slope over here at 2 and flipped it. Let's do another one. These are really quick once you get the hang of it. Okay, you want to find the derivative of the inverse of f at 5. What's the first thing you got to do? Set it equal. And this you can just do guess and check. X cubed plus 5x minus 1 equals 5. Think of a number mentally, plug it in for x, see if you can get the sides equal. Easy numbers. Like that's what they tend to do on the AP, so you don't need a calculator. Think of some basic numbers. Plug it in. And 0 doesn't work, because that would be -1 equals 5. You got it? Say it again. 1 works, right? You see that? If you plug 1 in for x, you get 5 equals 5. Okay, that's our first step. What's the second step? Derivative, very nice. So we find the derivative of the original function. And what's our third step? Plug in the x we found, so we're going to plug 1. So we're going to find f prime of 1. What's that? 8. So we were asked to find the derivative of g at 5. What do we know it has to equal? 1e. Right? It's always the reciprocal. When you do the homework, I think you have 5 problems. These you could solve without a calculator. There are the last 2, that very first step, you're not going to be able to solve it. They're not going to be nice numbers. Do you know how to solve an equation on the calculator? No? I think if you go to, I have this on here. If you skip the next example, I think I have one where the function is x cubed minus 4x squared plus 7x minus 1. What is that, example D? Okay, and they want us to find the derivative at x equals 1. So you have to find out, you have to solve the equation x cubed minus 4x squared plus 7x minus 1 equals 1. One way on the calculator to solve an equation is to put one side in y1, the other side in y2. You had to have seen this before, right? No? How do you solve an equation? Well, when they equal each other, what are the graphs going to do? They're going to intersect, right? So what you do is you find out where they intersect. Zoom 4 works nicely for this guy. So you're looking for this x coordinate. So what you do is second calc, option 5, and it's going to ask you first curve, and it's going to show you the equation. You press enter. Second curve shows you the equation. You hit enter. Yes, that's close. Enter. And it's showing you that they intersect. Oh, mine's already abbreviated. 0.349. Now yours might be going out if you didn't put it on 3, if you have it on float. But it's solving the equation. Now we got to plug that into the derivative of the function and flip it. Now if you're really lazy like I am, if you find a value on your calculator and you don't feel like writing it all down and everything, you could just store it into alpha A. You ever do that? You find an answer on the calculator? We'll do more of this, but you can leave the screen and hit store alpha A, enter, and it stores it there. So now I can just get the derivative of the function and flip it. I could plug it into the derivative of the function. I could do math 8. The function I stored in y1, vars, y vars, function. So take the derivative of y1, comma x, comma, I don't have to type that in. If it was long, that'd be a pain. I could just say alpha A. So I found where they intersect, and I called it A. You don't have to do that. I'm just being fancy. And now I'm telling the calculator, plug that value into the derivative of the function that I have stored in y1. And then do you know how to flip it without having to do much work? What button do you press? Because I want to flip that. I heard it. X to the -1. So you can do it all in there. But it's the same process. It's just, you know, when you set your value equal to the function in the beginning, you solve for x, um, you're just going to find out where the graphs intersect to solve it. But everything else is the same. X to negative 1 is right here. So that means take the reciprocal of. In this case, the negative 1 means reciprocal of. So when it's on a function, it means the inverse function. All right, for that. I got to show you answers to the homework. I promised. Yeah, what was this? I might have to write these out for you kids. I know a lot of people for number 1 got 0, so I'm kind of interested to look why. You got 0 too? All right, I want to look at that one. Number 1, a lot of people got 0. It's supposed to be negative 1/8. Oh, wait a minute. People that got 0, did you get first derivative or second derivative? Okay. I'm just trying to use this. Yeah. For people that weren't here on Friday, when you get the second derivative, you take the derivative of the first derivative. But if you have any dy dx in it, you have to replace it. You have to, you know, with whatever dy dx equals. That's where that came from. Oh, don't give a sad face. I also had a lot of questions on 15. Is it all right if I scroll up a little or no? Just to get the top off. Just make sure you got 13 and 1 written down. Okay, we're 13 and 1. Okay, when you get the derivative for 15, they ask you, okay, where's it going to have a horizontal tangent? Well, horizontal tangents occur when the derivative is 0, when the numerator is 0. So when x equals 2. But to get the y coordinates of the points, you got to go back to the original function. So the points turn out to be 2, 0, 2, negative 4. But horizontal tangent, that's when the derivative is 0, so the numerator is 0. For the second part, where are the vertical tangents? Well, that's when the denominator of the derivative is 0. So that tells you y is negative 2. When you plug negative 2 into the y of the original, you get 6 and negative 2. So the points where it has a vertical tangent would be at 6, negative 2, and negative 2, negative 2. So that was a little tricky, that number 15. Can I go to 1 so people that are, you could always look this up later. I got it on there. Number 1, it looked like when I checked people, you had the first derivative right. Low d high, less high d low. It looked, because you got 0 too, right, Ashley, for this one? And you put in, oh, you had a minus. No. Yeah, you had a minus y there instead of a plus y? You did. Well, did you get, you had to substitute in for negative dy dx, you put in y over x? Because dy dx came out to be negative y over x. So when you substitute in, oh, yeah, but still, if you got the numerator 0, you would get 0. Because you should have y plus y, or 2y, over x squared for the second derivative. Then you plug in the negative 4 for the x and the negative 1 for the y, and you get 1/8. I'm sorry, negative 1/8. And I did want to show you for the number 7 someone had asked me. Oh, shoot, I erased it. Okay. Was it 7? Yeah. All right, if I don't finish it, I'll have to So you had, this is xy to the half. So when you take the derivative 1/2 xy to the negative 1/2, derivative the inside, you had to use product rule. X dy dx plus y times 1. The derivative of the other side would be 1 minus 2 dy dx. You have to distribute before you can separate. So you need to distribute. You'll have two terms on the left after you distribute. One will have a dy dx and one won't. So you're going to have 1/2 xy to the negative 1/2 times x dy dx plus 1/2 xy to the negative 1/2 times y equals 1 minus 2 dy dx. You would have to get the dy dx on the left, so this term would be on the left, and this term would be on the left. The other terms are going to be on the right, then you could factor it out and solve for dy dx. And I'll finish it for the video so you'll be able to see it. So you have 1/2. Bye, guys. Thank you. You too. 1. Wow. Factor out the dy dx. So we have 1/2 xy to the negative 1/2 times x plus 2. And then we're going to be able to divide. Oh, okay. Well, that's not bad. I'm going to finish it up because maybe Jillian will want to know. She's at home today. And then we had to plug in 4 for x and 1 for y. So the derivative evaluated at the point 4, 1 is going to be 1 minus 1/2. That would be 4 to the negative 1/2, which would be 1/2 times y, which is 1, over 1/2. 4 times 1 to negative 1/2 is 1/2, times x, which is 4, plus 2. So we get 1 minus 1/4 is 3/4, over 1 plus 2 is 3, which equals 1/4. And that is it. And going back. So to summarize, as far as getting the derivative of the inverse of a function, first set f of x equal to, in this case I call it a, and solve for x. Oops. Hi, come on in. No, I'm just talking to myself. And solve for a. Second step, find f prime of x. Third step is plug answer from part 1 that we just did, solve into f prime of x, and finally take the reciprocal. And that is it for today.